Okay. Sorry about that. Alright, so that should have fixed it. I'm sorry for that. I guess I'll just start over. So we went over concavity in the first video, and concavity is very loosely, I'll erase all this stuff just to sort of make it more clear. Concavity is literally the rate of the rate. So if we look at a function like y equals square root of x, which I've just shown here, our concavity is saying is the slope of our tangent line increasing at an increasing rate or decreasing rate? So essentially, let's say I have some point A here and some point 2A. If we're going from A, and so let's say that this is B and this is C. So if we're increasing at a decreasing rate, I'll just call this C and this B. If we're increasing at a decreasing rate, C should be smaller than B, or we're essentially increasing less for each set amount, which would be concave down. So that's concavity. It's describing the rate of change of the first derivative. And so, as stated, concavity is the second derivative. D squared y dx squared. This is how it's written. You'll also see this, but I find this to be slightly more clear. And then so we also went over points of inflection, and this is basically, think about y equals sine x. If I draw a very quick graph of this, you can see that we're going from concave down here to concave up over here. And so a point of inflection describes where we go from concave up to concave down. And then so we talked about how to determine a function's concavity. And I gave you sort of a very easy way to remember. If we are concave up, our second derivative is positive. And if we're concave, and if our second derivative is negative, we're concave down. And so you can sort of remember this picture right here. Up is happy, down is sad. Okay. Again, if anybody has questions, you can feel free to ask. Otherwise, I'll just sort of keep going over stuff. Alright, and then so we talked about how to determine points of inflection. And here we're setting our second derivative equal to 0, solving for x, and then doing something similar to the first derivative test, but with the second derivative test, which is this. Seeing as we have no questions, I'll quick do one of those. Find all points of inflection for y equals sine x. Okay. So to find a point of inflection, just change my pen color here. So to find a point of inflection, what we need to do is we need to set our second derivative equal to 0 and solve for x. So first we need to actually get the second derivative. The derivative of sine is cosine. Definitely one you should know off the top of your head. And then we need to just take another derivative. And the derivative of cosine is negative sine. Okay, so now we need to set this equal to 0 and solve for x. Alright, so where does sine equal 0? Well, if you think back to the unit circle, sine is y. So our sine is going to equal 0 when x equals 0 and pi. And also at 2 pi. But it would also equal 0 at 3 pi and at negative pi. So we can actually say that x equals pi n, meaning that for any number n times pi, the sine of that will equal 0. So this is something you should be familiar with. Because sine goes on forever and ever, but it's periodic, meaning it repeats itself, we can sort of say that we have some n where that value that we're looking for is repeated. Okay. And so now we need to do the second derivative, not the second derivative test, but we need to test to make sure that this is in fact a point of inflection and that we're not sort of, sorry about that, we're not sort of doing this, where we're staying at concave up, but our concavity reaches 0 at some random point. Alright, so here we can just do any value n. I chose n equals 1 for pi. Here I know that 0 is going to give me 0. So, and again, you know, this is sort of going infinite like this. So I'm not going to pick values. So I'll pick values between pi and 0 and pi and 2 pi. So pi halves and 3 pi halves is easy. I'm sorry, this should be down here. This is what x equals. And this is what our second derivative is equal to. Okay, so the value of the sine of pi over 2 is 1. So again, we're plugging this into our second derivative, which is this. So sine of pi over 2, 1 times negative 1 is negative 1. Sine of 3 pi halves is negative 1 times negative 1 equals 1. And so we know that this is an inflection point, but we'll pretend this is the AP test, so we'll speak derivative here. Since d squared y dx squared equals 0 at x equals pi, we'll say pi n. D squared y, and d squared y dx squared is less than 0 at pi halves, and d squared y dx squared is greater than 0 at x equals is less than 0 at pi halves. The point pi n, comma, and then sine of pi n, we can choose any n. We'll say n equals 1, sine of pi, well, the sine of pi is 0, is an inflection point. Okay, so if we have any questions on that, you know, feel free to leave a comment. Otherwise, I do see that we had a question, so I'll move on to that. But, you know, at any point, if you're confused on what I just did, finding the second derivative, be sure to ask a comment. Okay. So, question is, I assume that your question wants me to include 0 in pi, so that's what I'll do. But if it doesn't, be sure to let me know, and I will change that. Okay. So, we want to find our relative extrema, so we need to find our critical points, or where dy dx equals 0. So first we have to actually find dy dx. And before we do that, let me make a point that I've made before, but this is an important one to know. These are equal. So to take the derivative, whoops, but also these are not equal. Alright, so just a quick note. So to take the derivative of this, we can just do the chain rule. So 3 sine squared x, and then we just want to do the chain rule, so the derivative of sine is cosine. Alright, so now we need to set this equal to 0 and solve for x. So this is sort of already factored, or it is already factored. If we set this equal to 0, okay, so we can split up the factors, set those equal to 0. So 3 equals 0 is extraneous. Sine squared x equals 0, and cosine x equals 0. Okay. So now we just need to basically solve for these. Alright, so it's asking between 0 and pi. So where does sine equal 0 between 0 and pi? Well, at x equals 0 and x equals pi. Cosine equals 0 at pi over 2. And again, this is, if we go back to the unit circle, remember, cosine is x and sine is y. So x equals 0 here at pi over 2, and y equals 0 here at 0 and pi on the interval 0 to pi. Okay. So now we need to do our derivative tests, and for the sake of this live stream, we just covered the second derivative tests. We will do that. So first we have to find our second derivative, and here we have to do the product rule. So sine squared x times cosine x is really what we're doing here. So I'll take the derivative of cosine to start, which is negative sine. So this is negative 3 sine cubed x plus 6 sine x cosine squared x. And if you're confused as to how I got that, I'm doing the product rule for this right here. If you'd like me to walk you through that, I'd be more than happy to. Just leave a comment. Okay, so we now need to plug these values into our second derivative. So if you remember our first derivative test, we did like this. Well, that's how we did the first. The second is much easier. So x equals now we just have a table. So here we'll put in our critical values. And okay. So plugging in 0, the sine of 0 is 0. And so this is going to give us 0, so that is inconclusive. The sine of pi halves is 1. Negative 3 times negative 3 is negative 3. Plus, and then I know that the cosine of pi halves is 0, so the second term is going to be 0. So that's just negative 3. And at pi, I'm going to get the same thing. Sine at pi is 0. So our second derivative test is inconclusive, and we have to do more work. Okay. So now we'll do the first derivative test. This should be pi halves. Alright, so we'll say minus pi over 4, pi over 4, 3 pi over 4. Okay. And now we just really need to worry about the sign of our first derivative. So at negative pi over 4, that's really saying 11 pi over 4. So the sine of 11 pi over 4 is going to be negative root 2 over 2 squared positive times cosine of 11 pi over 4, which is positive root 2 over 2, so this is positive. At pi over 4, sine and cosine are both going to be positive root 2 over 2, so this is positive. So 0 is a critical value, but it's not a relative extrema, because essentially we're increasing and then increasing. So what that might look like is, say, here, and then we're horizontal, and then we're back to increasing. Okay, so at 3 pi over 4, my sine is positive, positive root 2 over 2. Cosine is in fact negative negative root 2 over 2. So this is going to be negative. So pi over 2, I'm sorry, I already did pi over 2. Should just be pi. That still works. This will say 7 pi over 4. Okay, and it's still going to be negative because the sine of 7 pi over 4, 7 pi over 4, it should be 5 pi. Okay, because this is 7 pi over 4. Because our sine is going to be negative, but we're squaring it. So those are going to cancel each other out, but our cosine will still be negative. So our derivative is negative. Okay, so we can say since we need to speak derivative, since pi over 2 is, I'm sorry, since the point pi over 2 comma sine of pi over 2, remember, is 1. Cube that, so it's just 1, is a relative. And now let's think about it. We're concave down because we're less than 0. And if you remember the picture, or I gave the answer away, but what I meant to say is our second derivative is negative, so remembering the picture, concave down. So second derivative is negative or concave down, that means it must be a relative max. So it's a relative max. Okay, and now let's do the same thing for our other one. So since dy dx equals 0 at x equals pi, and dy dx is greater than 0 at x equals pi over 4, and dy dx is less than 0 at 5 pi over 4. The point pi, sine pi is 0, pi comma 0 is a, and I'm not exactly sure myself, so we go from increasing to decreasing, so relative max. And that might seem strange to have two relative maxes but not two relative mins. And sort of what this would look like is we're sort of going up and then we go back up again, and we're sort of always increasing. Alright, so hope that answered your question. If you guys have any more, be sure to ask in the comments. Otherwise, I can go over what we did in our other video, unrelated rates. And so this This stuff is not straightforward at all. Unlike most things in calculus where, you know, like let's say you had y equals sine x cosine x, and you wanted to, the problem was find dy dx. This is very straightforward how you would do this. This is just the product rule. Some of you might use an identity here, but it's very straightforward how you would do this because you have sort of known rules. Like here, this would be the product rule. So this is something that's very common in AP Calc. Is, you know, you sort of know right away how you have to do something, and sort of the devil is in the details, in that the arithmetic might get complicated or it's hard to simplify or something like that. Related rates, this is not really the case where we have something, a simple formula like this, although I think it can be broken down. So the idea of related rates is that we have a known quantity and we want to find the rate of another quantity. So the example I gave is that air is being pumped into a spherical balloon at a rate of 3 centimeters squared per second. When the balloon's radius is 25 centimeters, how fast is the radius increasing? So essentially, from the rate of change of the volume, I want the rate of change of the radius, and that's the idea of related rates. Okay, so I said that the best way to do this is first to draw the picture, then write out your formulas, and then we implicitly differentiate, and then we can plug in our knowns, where eventually we'll find what we're looking for. But this is a very easy one. And so I gave a little bit of a tougher one. Where if you just wrote out the formula and did the derivative, you would end up with 2 unknowns, and that wouldn't solve the problem. And so here we have to substitute variables, where I was substituting r equals h over 2 in for r, and then we end up with 2 variables. I can take my derivative, plug in my knowns, and then find my unknown. And so sort of a giveaway that you have to do that is this sentence. They're not going to tell you that unless you needed to know that. It's also a giveaway if you have 3 variables and you're only given 1 rate of change. That's also a signal that you need to solve for 1 variable before you take a derivative. But this is by no means easy, and so I think the only real way to get better is to sort of implement that advice in your practice of these. And although this isn't like a main thing on the AP Calc test, it is important. Okay, and then we capped off with the challenge problem. Okay, so if anybody has any questions, be sure to ask away. Otherwise, I can just sort of do random stuff. Okay. I think it might be worth doing the challenge problem. Okay. So here we want to draw our picture. A ladder 15 feet long is leaning against a wall. The ladder then slides away from the wall at a rate of 3 feet per second when the ladder is 9 feet from the wall. How fast is the ladder moving down the wall? So what I did was I drew the picture. I'll make this a little more clear for you. Make this, wow, that was terrible. Okay. This is the best you're gonna get. So here's a ladder leaning against a wall that's 15 feet long, and our distance is 9. Alright, so the length here, I'll just call it L. And just right off the bat, I'll solve for L. And here I know that L equals 12. I just recognized this as a 3, 4, 5 right triangle, but if you actually did the arithmetic, you would find that L equals 12. Okay, so now the problem is asking how fast is the ladder moving down the wall. Okay, so it might be worth writing this out as width and 15 I'll just call, I don't know why I made that L, to be honest. This will be height, this will be ladder. Okay, so if I write out my formula and then take my derivative, again, this is all implicit differentiation. And now I want to plug in my nodes. So the first thing I want to point out is that dl dt equals 0. That's the rate of change of the length of the ladder. And our ladder isn't changing length, it's staying 15 feet long. So I can say that this right-hand side equals 0. The rate of change of the height is what we're trying to find. And our height equals 12, as we just showed. Our width is 9, given to us in the problem, and it's sliding away at a rate of 3 feet per second. Alright, so now we just have to solve for dH/dt. 2 times 9 is... Okay, well, 2 times 3 is 6, 6 times 9 is 54. So negative 54 all over 24. Let me just quick see what that is in decimal. 54. Okay. And that is 2.25, which is 9 over 8. No, 9 over 4. I apologize. Negative 9 over 4. Okay. And now we have to answer the problem. So the problem asks, it's asking how fast is the ladder moving down the wall. So this answer, minus 9 over 4, isn't really answering that problem. So we have to say the ladder moves down the wall I'll give myself some more space. give me a second. The ladder moves down the wall at a rate of minus 9/4 feet per second. Okay, but now let's think about this. So what does the dH/dt equals minus 9/4 represent? Well, that says that our height with respect to time is decreasing at a rate of 9/4 feet per second. And the problem is asking how fast the ladder moves down the wall. And so if it's moving down the wall at a negative rate, that's sort of a double negative. And so this would imply that the ladder is actually moving up the wall. It's decreasing negatively, meaning it's increasing. So we actually don't want that negative. So we say that the ladder is moving down the wall at a rate of 9/4 feet per second. Easy to get mixed up with that, but if you do have a question on that, or why that's the case, be sure to ask in the comments. Otherwise, again, if you guys have questions, be sure to let me know. Okay. So I'm trying to think what else we might want to do. So we went over what we did in last week's video, and we went over okay, so I guess we can do one on concavity again. So I just sort of mentioned in passing that, let me draw a little bit of a better picture. Actually I'll switch colors. Okay. Alright, so I sort of mentioned that if inflection point Alright, I want to sort of walk through why inflection point makes the second derivative equal to 0. And to understand that, we have to look at sort of what the second derivative test is. It's concavity. And so one way to look at it would be to say that if we go from negative concavity to positive concavity, at some point we have to hit 0. And that would sort of be similar to the mean value theorem. But there's another way to think about it, in that if the second derivative is 0, we have no concavity. And so that should make sense as an inflection point. Also note that at inflection points, this is not to say that the first derivative equals 0, only the second derivative. And so if you sort of think about this, if f prime of x equals 0, that means our tangent line looks like so. And, you know, we can pretty clearly see that if my tangent lines are doing this, I'm sorry, it should be, whoops. If my tangent lines are going like this, it's pretty clear that at my inflection point, my slope is not going to be 0. But that begs an interesting question. We'll say if a comma b is an inflection point, what does f prime of a equal, or what is our slope at an inflection point? Is it one thing? Does it have multiple values? So let's see if we can answer that question. Before I get started, I want to say that we're going over integrals next week, and that one way to tackle this would be to sort of do this. Although now that I think about it, you can't easily integrate that. Okay, never mind. But get excited, because we're doing integrals next week. Okay, so what does f prime of a equal? What is our slope at an inflection point? So first, let's find something with an inflection point. Alright, so let's try this. Alright, so x equals 0 is a possible point of inflection, and y equals x cubed. Okay, so x equals 0 is an inflection point. Well, what is our slope? Plugging that in, dy dx equals 0. Okay, so here our slope is in fact 0. But pretty quickly I'm going to see that that might not always be the case. So what about x cubed plus 2x? This is going to be plus 2, and that'll disappear. Okay, so what I'm doing here is now my function is y equals x cubed plus 2x. My first derivative is now 3x squared plus 2. And my second derivative remains the same. But at x equals 0, plugging this into my derivative, dy dx equals 2. So in fact, at a point of inflection, our slope can actually change. It can be different. Unlike a critical value where it's sort of always 0. We just saw an example where at a point of inflection, our slope is 0, and at another one, our slope was 2. Sort of interesting to think about. Actually, a lot of times you'll see that at a point of inflection, we have a slope that is undefined. So, like, if this was our point of inflection and our tangent line is vertical, then dy dx is undefined. And this is an example of something being continuous but not differentiable. And so the answer to our question is many things. It can equal a lot of different things. There's no one slope for all points of inflection. Alright, so if you have a question on literally anything relating to AP Calculus, or maybe you need some life advice, go ahead and just quick leave a comment and I'll try to help you out as best I can. But seeing as we have no questions, I can just sort of mosey around with some other stuff. Okay. Alright, so to the 4 people watching, I'd also add that, you know, you might not have a question, but if there's something you want me to go over, I'd be more than happy to do that as well. Otherwise, I'll just sort of jump into some other things that we've gone over. Okay, so say y equals 5e to the 5x all over x. Find relative extrema. Alright, so again, we want to find where dy dx equals 0, so let's take a derivative. And this is the quotient rule, excuse me. Derivative of the bottom times the top minus the bottom times the derivative of the top all over the bottom squared. And so if we go back to here, we can see that in fact I made a mistake. Okay, so this should be the derivative of the top times the bottom. I apologize. 25x e to the 5x. The derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared. And we need to find where this equals 0. So I can sort of split this up. I'll say if I multiply this through by x squared when it equals 0, that's just going to give me this. And now I can factor out 5e to the 5x. Alright, so where does 5e to the 5x equal 0? Well, when x equals, Okay, well, sort of getting ahead of myself. I'll split this up. Okay, so where would this equal 0 at? What x value? Well, at x equals negative infinity, that would go to 0. However, we're looking for real numbers here, so this is extraneous. This, however, is not. This is x equals 1/5. But I want to remind everybody that when we look for critical values, we're actually checking where the second derivative equals 0, but also where it's undefined. So this would be undefined as well at x equals 0. So these are my critical values. So that's easy to forget that you need to include x equals 0. But that's actually very important. And so now let's do the second derivative test. Just kidding, let's not do that. And so I sort of talked about this in our last video. There are times when you want to do the second derivative test. If dy dx equaled 3x, this is an obvious second derivative test. But here, I'm going to have to do the quotient rule again. I'm going to get a really big fraction. So it's probably best if we did the first derivative test. Okay, so at -1, my x squared is just going to become 1, so we can forget about that. 25x e to the minus 5. So that term is minus 25 times, over e to the 5th minus 5 over e to the 5th. So that is going to be negative. At 1/10, this is sort of harder. So let's pretend that this is a calculator problem. You could work through that and sort of figure it out on your own, but for the sake of simplicity, we'll pretend that this is a calculator problem. Alright, so I've got my calculator and I'm just going to plug this in. I find that the best way to plug things in on your calculator is if you hit the y equals button. If you're on the TI-84 or 83, you type in your function. So I'll do that right now, even though you can't see, but I'm typing dy dx into my y equals on the calculator. Okay. And then I hit second graph to go to the table, and I just plug in 1/10 for x. And this gives me a negative number. Okay, so 0 is nothing. And at 1, I'm going to get a positive number. If you think about it, this is going to be, everything is over 1, so we can forget about the x squared on the bottom. 25e to the 5x minus 5e to the 5x. That's positive. So it turns out that 1/5, we're going from decreasing to increasing, is a relative min. Okay, so we're about out of time on our live stream. I want to thank everybody who tuned in. Let me just get some more space here. Thanks everybody for tuning in. We'll have new calc videos out on Tuesday and then another one on Thursday. You can be sure to follow us on Twitter at LearnAP, or you can like us on Facebook at LearnAP. Okay, so other than that, that's about it for our calc live stream. We're going to pick back up in just a minute with our chem live stream. So if you're in chem, be sure to stick around. That live stream will start very soon. Other than that, thanks for tuning in, and I'll see you in our next videos.